You might have seen this device before. This is the AMD Ryzen AI Halo. It shares the name with the Strix Halo chip that's inside there. It's an APU, so it's got the CPU, the GPU, with 128 gigabytes of memory that can be shared between the two to do AI work. And in my previous video, I already covered the details about this, and I ran a bunch of benchmarks comparing it to the NVIDIA DGX Spark, as well as the previous machines that had this chip in it. But this one is the smallest. And according to AMD, on a tiny box like this that you can fit into your pocket, well, maybe, you can run models that are up to 200 billion parameters in size. In the last year that this chip has been out, AMD has done a lot of work to not only get support going for it, but they also came out with these playbooks that you could easily follow along to generate images, videos, text, use them as coding assistants, something you'd all be interested in probably. And in this advanced section, you can now cluster two of them. So you'll be able to potentially run models that are about 400 billion parameters. Now, two computers don't automatically become one larger computer. The model must be split somehow. The GPUs that are processing that data must continually exchange data while generating. And on this machine, that communication happens over Ethernet, because this 10 gigabit port is the only thing we have to connect them to. So the question is, can these two actually function as one practical AI system? Or will the network between them ruin the entire idea? According to AMD's playbooks here, you can use two different methods to cluster them together. One is using Llama CPP with RPC, and that's basically remote procedure call. And Llama CPP is a very popular tool. Llama, if you've heard of that, LM Studio, all use Llama CPP under the hood. And you can run Llama CPP directly, which is what this will do. Well, it's got RPC built into it. We'll go into that. And RCCL, RCCL, it's pronounced Rickle. I don't know. It's kind of like NVIDIA has Nickel NCCL, so this is RCCL. RCCL uses VLLM and Ray, another two key pieces of technology with tensor parallelism. Basically, it's a way to split up the model. I've discussed this in many videos in the past. I won't go into the details of that, but this will use that technology. So there's two different ways of doing it, and both methods combine the 128 gigabytes here and 128 gigabytes here to give you 256 gigabytes of available memory on the two machines. It's actually a little bit less than that because you still need a little bit of memory for the operating system. But both of these methods call for a proper 10 gigabit Ethernet network. However, you can't just take a cable and plug them in together like that and have that work. That's just not going to do it, even though each one of these has a 10 gig port. AMD's instructions for both of these require a 10 gigabit Ethernet switch to be used between the machines. So yeah, that's not gonna work. So before I can build this cluster, I need to sort out that network switch between them. These Ryzen Halo machines are now available at the Micro Center, which is their exclusive retailer. This is Dan, by the way. You met Dan before in previous videos.
Nice to meet you guys.
Say something about his hair.
Yeah, please do. I changed it up this time.
Dan, take us to the switches, if you don't mind.
I don't mind at all. Probably gonna be in a little bit of a fancier spot. In theory, this is the switch area. In practice, like I said, I think the switch you want is probably gonna be hidden somewhere. I can make it appear.
Let's make it appear.
With movie magic.
I know where it is.
Oh, you do?
Yeah.
What? When are you submitting your application?
Dude, it's in the Unify section.
Yeah, but I mean, I figured, but I thought it was gonna be like one of those boxes that we hide up in another aisle.
But we'll find it, don't worry.
We will find it. Movie magic is happening, I promise.
In the back of the scenes.
Oh, was it just out there?
Oh, okay, thank you. They put it in a different box now.
But it works. That's what matters, right?
Do you wanna, like, hold it?
See as a size comparison so they can see that I'm actually bigger than the box.
You are bigger than the box. You couldn't fit in that box.
I could not.
This is that Flex XG switch that I picked up for Micro Center, but actually it's just an empty box. I picked that up last year and I already had it. It's right here. Thing is, back then I didn't understand why it had 4 10 gigabit ports and one 1 gigabit port. Well, now I do. It's actually perfect for clustering because you plug in your cluster up to 4 machines. In this case, we're doing just 2 into the 10 gigabit ports, and the 1 gigabit port, that's just going out to your network so you can manage your cluster. Plus, it's completely silent because There's no active cooling here. It's all a giant heatsink. It's pretty heavy too. That would take care of the network, but there's still one little issue. I can't cluster these machines the way they are now. They don't match. The Halo I tested in the previous video came with Windows, and the second one had Linux on it. AMD's documentation for beginner and intermediate, all these different playbooks you can do on Windows or Linux, but the clustering playbook is only on Linux. So I need both machines set up the same way. Instead of configuring the second machine from scratch and hoping I reproduced the environment exactly, I just simply cloned the Linux installation onto the Windows machine's SSD. That gave me two identical starting points with the same drivers, the same AMD software, and the same exact configuration. Of course, I knew we needed to download models onto it, so before I cloned it, I made sure that one of the machines had models on it, so I don't need to download the models twice. Also, cloning the drives also cloned the machine's identity. So before I connected them up, I had to make sure that the host names were different. One became Halo 1 and one became Halo 2. Turn that on. Yes! It's Ubuntu. That used to be Windows. Huh? And we're in, baby. Nice. Now I have two matching Linux machines, and yeah, I'm not gonna put them on top of each other because the vents are actually on top and on the sides, so these kind of have to be spread apart a little bit. Just a quick little test. I got iPerf 3 on server 2, Halo 2, and iPerf 3 on Halo 1, just to test the network bandwidth between the two, and it looks like it's coming back pretty much to its maximum capacity, 9.41, 9.44. Yeah, that's as much as we're gonna get for a 10 gig network. Network is ready, software is ready. Now it's time to try this playbook. First, we're going to try RPC, which is under Advanced, and right here, clustering two Ryzen AI Halos with RPC. I already went through some of this installation here. I did this step, this step, this step, and this is interesting right here. Very, very interesting. AMD TTM. This lets you find out how much shared memory there is. And I got bitten by this on one of the machines. I'll tell you why. If we run this, you'll see that I have a total system memory of 125. It's 128, but you know, there's some for the system. And total current TTM pages limit is 120 gigabytes. This is the reason why we're using Linux instead of Windows. Windows limits this to 96 as maximum. Linux can go up to 120, but not by default. You have to run this command right here. It's part of the playbook in order to give it or allocate 120 gigabytes, which means the GPU can use up to that much, allowing you to fit models theoretically up to 240 gigabytes in size. Now, the issue that I ran into was really funny because, well, it wasn't that funny. I didn't think so at the time because it took me a little while to figure it out. The Windows version automatically sets it to 64 gigabytes. And this is not something that you can discover in the BIOS. In fact, I went into the BIOS and tried to find that setting like some other Ryzen machines allow you to do, but it wasn't there. It's not exposed in the BIOS. You can only modify that setting using the AMD Ryzen AI Developer Center. Even after I put Linux on that box, I couldn't change it in the BIOS. I couldn't change it using this AMD TTM Set 120. In fact, I ran that and it did not work. The system was limited to 64, and Llama CPP RPC was detecting only 64, but I'm getting ahead of myself. So in order to fix that, you need to go into the settings tab of the AMD Ryzen AI Developer Center, which comes with the Linux installation here, and that software allows you to tweak the GPU memory allocation. And as far as I know, that's the only way to do it. Now, you also need to determine the name of the interface. Unlike the DGX Spark, which has a lot of interfaces, this one only has one. There it is, right there. And most likely yours will also have that same name. Having the interface name will allow you to confirm the speed that's available to you. So that's 10 gigabit right there. So we're good with the connections. Now, this gives you two installation options, Lemonade SDK or manual source build. I actually like doing the manual source build. It's not that hard. You just go to Llama CPP's GitHub, and it's good to poke around in here. What's good about this project is that it's so popular that it kind of had to be really well documented. And if you're doing any sort of AI work on your machines, you should be familiar with these steps. Just go on the GitHubs and use the quick start there and do the build. Do it right now. And you can just keep going through the playbook. I don't want to bore you with all the steps to go through this because it's pretty much verbatim. You just go through these steps one by one. I did that and I want to share the results. One more thing to notice here is the playbook uses GLM 4.7. See, I told you it was verbatim. I'm reading it right here. It's a 358 billion parameter model in the Q4KXL quantization from Onslaught. that's actually not what it is, because here they tell you to include the UD-Q4KXL, and that's what I use, the UD version, but the Q4KXL and Q4KM will also work. The KM is what I usually use, so I was wondering, why do they have UD-Q4? Well, this model is Unsloth's GGUF, and the difference with UD, that just means Unsloth Dynamic. So if I back up here, under GLM 4.7 GGUF, you have all these different quantizations that Unsloth was nice enough to quantize for you, so all you have to do is just download them. Instead of Q4KM, Q4KS, we're getting this UD Q4KXL. Unlike the other ones where it's a uniform 4-bit quantization, like the classic Q4KM, this one spends more bits on the tensors that matter. Attention, the router, embeddings, and fewer bits on the huge, rarely hit mixture of experts layers. And that's actually a good thing. For a 358 billion mixture of experts model like this one, it's supposed to be better and have better payoff for the quality per byte. Yet it's exactly the same size. I've talked about this on the channel before, and Bartowski is another quantizer, pretty famous on the internet. They all use like little techniques to tweak the quantizations to get more juice out of it. It's not just about running a bigger model, it's also running a higher quality quantization of a big model. But neither one of these quants will fit on a single 128 gigabyte box. The second Halo is what lets you serve a good quant instead of dropping down, I don't know, one of these IQ2Ms or IQ1S quants, which are probably gonna mess up your output. I made a whole separate video on the ladders going from different quantizations and what kind of output they produce. I'll link to that down below. I'm running it now, and with either one of these approaches, it takes a little while for the system to start up, but it's a lot easier with the RPC server, the way we're doing it right now. This is basically Llama CPP borrowing the second Halo's memory, and it's a much simpler approach. Halo 2 simply exposes its GPU as an RPC worker, and Halo 1 is like the root node that points to it and uses it. And it's up. It's doing the prefill, and there it goes. It's generating the text. We're getting about 8.2 tokens per second here. Remember, folks, this is GLM 4.7. It's pretty big. I'm gonna run ROCm SMI here, and wow, interesting. Okay, so VRAM is at 35%, and the power is only at about 43 watts. GPU is only about halfway utilized. This is only on one machine, by the way, so you'd imagine that it's the same thing is happening on the second machine. Oh, now it's going. Okay, so the GPU is back up to 100%. That's good. It's kind of bouncing around, probably between the decode stage and the processing stage. All right, it's almost done. By the way, I gotta take a moment to say this. You can't complain in the comments below that I don't ever do big models. Hey, big model. Another big model coming up shortly here. An even bigger model. Oh, here we go. 7.93, 7.69, 7.6. Within that range for the concurrency of 1, by the way. This is like basically chatting with this thing. And that's how many tokens per second we're getting out of this. Now, if we take a look at concurrency 4, which I also ran, we're almost doubling. That's not bad, actually. But it only goes up to a certain point with Llama CPP. With concurrency of 4 for TG128, we're getting 13, and for TG256, we're getting 13.5. But then if you raise your prompt up a little bit, a little higher to 2048, our concurrency of 4 falls back to 5.5 tokens per second. This is where this workflow breaks down. And with Llama CPP, you need a slightly different approach. I made a whole different video about that, how to handle Llama CPP with lots of concurrencies. Why do you need that? Well, if you're doing things like multiple requests at the same time with that kind of setup, if you're in a workspace with multiple people using it, or if you have an agent and if you're designing some kind of multi-agent architecture, then that matters. And I'll link to that video down below. But here we have a different approach to handling concurrency, and that's where the other workflow comes in. And that one's a little bit more difficult. And you say, well, why do I want a more difficult one, right? When this works perfectly fine. And if it works for your use case, go ahead and use it. RPC still lets you fit a giant model and run one conversation at a time, maybe two, but VLLM with Rickle, it's a different story. Your Ryzen AI Halo is already capable of running large language models locally, but clustering takes it further by combining GPU memory. You already know all this from watching the rest of my video, but in case you skipped around, this is a little refresher. But this playbook teaches you how to cluster two of them using RCKL, Communication Collectives Library. It's an acronym within an acronym with VLLM, and we're gonna run Quant 3.5 397B, which is a much bigger model than the previous one. Most of this documentation is the same as the one we just went through. You're getting the network link speeds, which we're fine with. You're installing a bunch of dependencies, setting your memory to the highest possible. Here's where things get different. VLLM containers, and this is going to use a Podman container and tells you exactly what to run to launch it. Now, this is going to take a while. In my case, for this large model, it took probably 15 minutes to actually launch it. It uses another technology called Ray, which is responsible for doing the multi-node communication. Yeah, there's a lot of stuff going on here. Let's see the results. Oh, on machine 1, you start Ray. On machine 2, you join the cluster, and then you serve the model using this right here. If you get one flag wrong, you have to start over and wait another 15 minutes. Don't ask me how I know. And this is why I use smaller models to try it with. Don't start with the large models first. Use a model with similar architecture. In this case, it'll be Mixture of Experts, Quant 3.5, but a smaller one. All right, so here we go. Llama Benchy, I'm gonna point it to this machine. And we're gonna run a couple of PPs, prompt processing 512 and 2048, and a couple of TGs, token generation 128 and 256 for concurrency 1 and concurrency 4. Here we go, this is the big one. Quant 3.5, 397B, and it's going. I can actually hear both machines. It's not breaking, it's going. You can also run ROCm SMI on each one of these machines. Here it is showing that 36% of VRAMs being used and 100% of the GPU. This also monitors the temperature for you and the power output. So we're using 60 watts, 52 degrees Celsius. It's a full amount of GPU usage, but not a crazy amount of VRAM usage. This is actually tensor parallelism at work here. TP equals 2. And we're using about 110 gigabytes per box here for a total of 220 pooled. Can you hear the machines? I can hear it. RCKL talking over the 10 gigabit link at about 7.81 tokens per second and up to almost 18 tokens per second for concurrency of 4. That's what I'm talking about. So if you remember group 3 from my previous video, the one that I kind of set up, well, this is for those of you that are in group 3. If you're going to be setting this up to do work, you have a couple of different approaches. And if you're going to be clustering multiple machines, then AMD gives you a couple of different options to do that. Llama RPC is simple. RCKL is a little bit more complicated, but it scales a little bit better. And it's like running a little mini data center at home or in your office. This is the technology stack that you'll use if you transition into bigger AMD infrastructure. Now, AMD also alludes to having 4 node cluster as well. And if you want to see my attempts at another machine's 4 node cluster with this very chip, watch this video here. Thanks for watching, and I'll see you next time.